Okay, this is a portion of the original talk that was unfortunately missed and didn't start the recording until partially through. So I'm going to add the material that we had talked about before. We're now in lecture 7, and we're going to be talking about Maxwell's demon today. So we've talked about the abstract several times, so I'm going to skip that. If you remember when I talked about the first computer I had ever used, vacuum tubes, in 1963. There were actually many earlier versions of computers, and one of them used delay lines. Now, the way in which this worked was that there was a tube of liquid mercury, and you would create waves of sound, changing electricity to sound, and the portion that the wave went through was a 1, and then the portion where it was no longer going through, it was a 0, and they were evenly spaced in between, and the material would go from the one end of the tube all the way to the other end. And of course, the sound of speed in the liquid tubes was much slower compared to the electricity, the current in the wires. So the material could be wrapped around and started over again, and the material just started the data that was in this signal around and around and around. So, and of course, the length of the tube told how long it took before it would go back to the beginning. But that was usually less than 1,000 times slower than the speed of electricity, which is about 1/4 of the speed of sound. So that was a memory technology in some of the earliest computers, and it was called an acoustic delay line. And in the 1940s and 50s, the memory in the EDVAC, EXAC, UNIVAC 1 were made of tubes of liquid mercury. Usually it's several feet long. As I said, the electrical pulses were converted to sound, sent and back to electrical in a continuous loop. At one end of the tube, there was a transducer to convert the electrical pulses to sound, which propagated through the mercury to the other end. And then another transducer converted the sound to electricity, sent it back to the beginning, and conversion to sound, which propagates much slower than electricity, slowed down the digital data a fraction of a second, causing in order of a few milliseconds. That's vastly long compared to 1/4 of the speed of light. So the device was a storage function. So that's one way to physically hold information, but of course there are many others. Well, if you're going to talk about how you get the information, you have to originate somewhere. An example is a songwriter. The information starts with someone, a songwriter, writing a song. And of course, there's more information added by a band in a studio, and maybe even a singer. Once created and copied, it can be distributed to the consumers. Now, economists declare that the purpose of money is for labor and material to be fungible. What is fungible? Fungible means that they give you a manner of exchanging things. So you can exchange labor for physical objects. And by setting a price for your labor and the price for the material that you're trying to get, you can use money, usually paper money here nowadays, to exchange your labor to objects, and that is what is called to be fungible. Okay, so is information fungible? It may be in the form of a modulated spiral groove around a photograph. That's one way to get sound out. Or it could be in the form of a strip of a magnetic tape in a plastic cassette. You would get the same material that you got out of the record or something very close. And then yet again, another very close copy of the material would be in an aluminized plastic disc with tiny holes in it, also known as a CD disc or disc. Okay. So nowadays, actually, most music is stored on a computer, and like all other kinds of data, this is a memory unit from a computer. We have two different kinds here. The current micro SD is a way of holding memory, but the little donuts that were shown with wires going through them, those actually, I also worked on a computer that had one of these, an old IBM 1640, I think was the name, or 1620, sorry, yeah, a IBM 1620. And the thing that was interesting about the memory that was done in these little donuts was that it was done not in binary, but in base 10. Now, unfortunately, that actually turns out to be somewhat wasteful, because if you do it in binary, you can get, 2 to the third is 8, 2 to the fourth is 16. So you have to use, you have to essentially throw away the other bits, but because you had these big donuts, you could actually just design them directly to make base 10. So the SanDisk here, 8 gigabytes, and there's probably about 10 bytes on the things that are woven together into the cores of the old memory. Now, the core memory was actually very, very robust. And it was used by the Apollo program, the computer that the Apollo both the lunar lander and the module that was in orbit over the moon, that was used from the Earth to the moon and from the moon back. Both of those computers were using these old cores. And the reason that they used them was because they were very, very stable. And there's a lot of stray radiation in space from the sun. So they were actually designed by MIT, and they brought in a group of, I forget how many hundred of women from a local factory that wove cloth, and they used them to make the computers that went to the moon. And they were an amazing group of women. They took their jobs very, very serious. They forced the MIT scientists that if they said that you weren't going to send and use the computer that they just finished, even if it passed all tests, it would be trashed. And they often did that because they felt they might have made some kind of mistakes, and they didn't want their guys, their boys, to die because they made a mistake. So they were pretty important women. Anyway, we live in a truly revolutionary age, the age of information. We're able to acquire, record, communicate, use so many different forms of information. It's amazing just how much kind of access we can get to. And we're able to translate information from one form to another easily and quickly. And we need to really understand how the concepts and principles of information work. The history of the information age goes back to the real revolution that started in 1948 in New Jersey, Homedale, at the research branch of the old Bell system, Bell Labs. This is the picture of Bell Laboratory, Murray Hill in Homedale. And this was a picture that had come in the Wall Street Journal, but it had the 42 picture, so I downloaded it for our talk. The event that started the information age was the publication of a long scientific paper in the Bell System Technical Journal. The paper was written by an engineer and mathematician, Claude Shannon. That paper fundamentally gave the elements of the new science called information theory. It's not inaccurate to say that the science was a new constitution for our age. It is impossible to exaggerate the importance of Shannon's ideas. Information theory has impacted far beyond the technology of communication and computing, which was primarily what Shannon initially focused on. Information theory is a profound unifying idea in many branches of science. IT plays a central role in contemporary physics, biology, finance, computing, artificial intelligence, and economics, just to say a few. So, what is information? Describing information is somewhat paradoxical. Information is certainly physical. To communicate or record information, we use a physical medium: sound, light, radio waves, electrical signals, idiomatic patterns. However, information is also abstract and beyond. The messages sent by our physical signals are not really identical to the signals themselves. They're observer or reader dependent as well. The Beatles songs are not just the record, not just the record. They are the emotional and other results unknown to the Beatles by various people who listen to it. This dichotomy allows the amazing transformability of information from pen to laser pulse to radio signals to sound wave, still somehow captures the rich essence of the material originally created. So Shannon was a real genius. He had a gift for abstraction. He could look at a complicated real-world subject, ignore the technical details, and discover the logical structure beneath it. During World War II in 1943, Shannon was in contact with Alan Turing. Actually, he had been in contact with Turing in 1941, but Turing was in London while Shannon was at Bell Labs. They were working on a project that made the ability for FDR and Churchill to talk without being overheard by the Germans. So, but Turing came to both Bell Labs and the Institute for the Advanced Institute for Studies in Princeton in 1943. And while he was there, he met and worked with Shannon and also with Johnny. So they were pretty amazing people. They found their work complementary, and he focused on the subject of communication after the war, although Turing focused on computing. So what is communication? How does it work? What is information? Like a detective, Shannon determined what information is not. And his first point is extremely surprising. Shannon realized that the mathematical idea of information is not isomorphic to meaning. Meaning is not a part of information. It's orthogonal to it. So he analyzed communication systems. The communication process is the same no matter what the message means. So it could be a formula, a photograph, a weather report, a nursery rhyme, or just a string of random numbers. Any of those things is all information. Information is not about the value or significance of a message. It's not about the meaning or value of a message, and it's not about the significance. Although those are obviously quite important, That's not what information is about. Shannon says it is two things. One, it is simple. It is information is a distinction between different messages. And two, it's about possibilities. A communicated message is one of many different possible messages. So the definition is that information is the ability to reliably distinguish among possible alternative messages. So the reliability and the ability to distinguish among a collection of possible alternative messages are the key portions of the definition of information. So we finally come back to the part that the lecture I had originally given with everybody else started here. So I'm going to stop now. Well, we're going to catch it at the beginning, or I'll have to say it again before I send it out, one of the two. Anyway, so the simplest two-valued message is called a bit, and it's short for a binary digit. So as an example, let's consider the Baudot code, invented in 1870 by the French telegrapher or telegraph engineer, Émile Baudot. The code was 5 bits. Because the French Patent Office and the patent law did not allow patenting the use of ideas, the patent was awarded for his keyboard called the Baudot, the Clavier Baudot. It was the code that was designed by Baudot was focused on minimizing operator fatigue. The machine that's shown on the right had just 5 keys, and the signals that came out of that were directly connected by wires to another office where the signals were interpreted and printed by hand for delivery. So this was the first code that was done. That code was later modified by Donald Murray, established for teletype machines in 1930 using paper tape. And the picture on the right shows a 5-bit paper tape as they were used in 1930. The vacuum machine that I used in 1963 used a 8-bit paper tape for input to the vacuum tube machine that I use. So it was just an advanced version of the teletype keys from 1930, machines from 1930. The keyboard duplicated the typewriter keyboard that was done earlier, and the device greatly improved the Clavier Baudot by punching paper tape and simultaneously sending the code to a Western Union office. So once the message had been punched in a tape, it could be folded or rolled, somehow collected in a drawer somewhere. And if you ever needed to send the message again, you would simply grab the original paper tape, run it through the teletype machine, and it would resend the information that was on there. And this was a great advance over the clavier bateau because you could use a device like the paper tape to save it and resend it to either the same place or different places as many times as you wanted to. Now, the Mori-Bateau code, also a 5-bit code shown in figure 9, but the redesign that it did from the original Bateau code, which was designed to minimize the fatigue of somebody typing on the clavier, this was designed to minimize paper tearing. And the worst of the codes for, of course, tearing was the 5-hole delete code. So the if you wanted to delete information, you would just retype on the same spot where you had the information, all 5 holes punched. And usually when you were using it, if you were writing programs or something like that, you would leave some space in the tape, then then write more section. And if you made a mistake, you'd go back and delete everything through that portion, go back to the blank part of the code, which would jump you to a new beginning point for the code, and then just keep typing the code from there again in the next place after you'd deleted all the mistakes that you'd made. Anyway, the delete code was used at the beginning, a sequence of them sent to identify the origination of a message. And this code, the Murray code, held sway until a 7-bit telebrinter code was called ASCII, was promoted by Bell Data Services in 1960 and standardized in 1963. And this was finally extended to 8 bits in the 1970s, and at last in 2020, literally right now, we've been using it for quite a long time, but the ISO 2-byte 16-bit codes are standardized on 143,696 graphic characters and 163 formatting characters, and also many of those 143,700 include emoji. So figure 10 shows the 7-bit ASCII code, and of course I'm not going to go on beyond that. So why did Bateau use 5-bit codes for the clavier Bateau machine? Why not 4 or 7? Well, by the way, one of the things I want everybody to do, please, is if anything is not clear, interrupt me and ask questions. It always frustrates me a great deal when people at the end say, oh, I'll have to watch the lecture again or read the stuff because I didn't understand something and you didn't say anything at the time, you didn't understand it. So please immediately ask any questions. There must be somebody else who's also thinking of the same question. So please always ask questions. So why not 4 or 7? The
You
answer,
have 5 fingers.
No, he was using 2 hands. He was using 2 uh, on the left hand and 3 on the right hand. So it wasn't because he was using 5 fingers. He was using 10 fingers, but only 5 of them. What can I say? The answer is more fundamental, especially in information theory. A code using 5 binary digits represents different messages by a series of symbols. But the code to preserve the information, that is the distinction between memory messages, which if we remember back, we're calling is the definition of information, the ability to reliably distinguish between messages. So no 2 different messages can be represented by the same code. So every message that you could possibly have has to have, from messages 1 to n, has to have some code symbol that matches it isomorphically. So that is, it has to be 1-to-1 and onto. So the number of code symbols can be no smaller than the number of possible messages, which we've said is m. The number of possible code symbols must be greater than or equal to m. Either the 1930 teletype codes or the Baudot codes were sending English letter, or in Baudot's time, French alphabet letters, but they were 26 letters. So they use, and they have a character for space between words. So M has to be at least 27. So how many 5-bit code symbols do we have? Well, suppose the 5th position is 0. Then the 4th position could either be a 1 or a 0. The 1 itself in the 3rd position could be a 1 or 0. The 0 could be a 1 or a 0. And so you just keep working your way down to the bottom, and you, trust me, this is 16. So for 0, you have 16 possible ways that you could write from 5 zeros to a 0 and 4 ones. Then you, of course, have the same identical structure starting at 1, the other possibility. So the possible number of code symbols using 5 bits is 2 to the 5th, or 32, which is 2 times 16. So in each position, there's 2 possible values, and 16 positions for 0, 16 positions for 1. 5 bits can create 32 unique code symbols. So if our messages are 27 possible alphabetic characters and space, we have enough room in our code symbols to make a mapping of each message into a unique code symbol. So that's why they used 5 bits. If they had 4, it would have only been 16, so you wouldn't have been able to handle enough. And if you had 7, 2 to the 7 is 128, so you'd have a lot of waste in the representation. 5 was enough to handle all 27 messages. So here is the way in which the Murray code works. You have a letter, and that is equivalent to a base 10 number, which can in turn be equivalent to a 5-digit 5-bit string. So 3 is, so if you read these across here, this is 2 to the 0, and it's either 1 or 0. So 2 to the 0 is 1. So this is 1. This is 2 to the 1. So 1 plus 2 is 3. That's what we get here. All of the other zeros on 2 to the 3, 2 to the 4, 2 to the 5 are irrelevant. Okay. The B is the equivalent of 25. So 1 plus nothing times 2 plus nothing times 4 plus 1 times 8 gives us 9 plus 1 times 16 gives us 25, and so forth for all of these. And again, the reason these are not in numerical order is because of the physical properties of the paper tape. And the design of the code was to minimize tearing on the paper tapes, not to make it the simplest design. Okay, as I said, if we got through with 4 bits, we'd only have 16. That's not enough. And if we had 7, we'd have 128. There'd be a tremendous amount of waste. There was another 19th century binary code. In fact, the first binary code that was designed, and it's called Braille, the writing system for the blind, created by Louis Braille in 1830s. Letters are patterns of raised dots used by touch, and they're in a 2x3 block of dimples. They can either be up or down, either way, but how many possible letters or symbols could be in the Braille one? Since we have 2x3 blocks, how many possible blocks are there?
64.
Yes. Okay, so there's 6 possible dimples in a block, and thinking of a dot as 1 and no dot as a 0 means that a Braille is a 6-bit or 64, 2 to the 6, 64 possible code words. That's a lot more code symbols for letters plus punctuation marks and some digits and other symbols. This is a picture of a Braille system it types out the, it shows the French word first on here. And so this is 2 by 3, 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 etc. Using computers introduces a new aspect of information. The computer's memory can be data, input, output, a record of a memory, scratch space for calculations, and lots of things. They're collected into blocks of memories, usually called files. However, the bits may also represent computer programs. That is, groups of instructions that tell the computer what it should compute. And a stored program is just a collection of bits. It's a file like any other. It can be moved, changed, erased, or copied. So computer memory has a two-sided nature, both data and program. Along with Alan Turing, who during World War II, while he was at Bletchley, designed the first automatic computer. He also worked at the Princeton Institute for Advanced Study in World War II, where John von Neumann actually came back from the Manhattan Project and worked with Turing for 2 months. And these two are probably the inventors of the modern computer. These geniuses both understood that data and program were identical and could be used interchangeably. Now, Turing's design was actually somewhat advanced compared to von Neumann's machine. If you remember, there were, for a number of years, I guess in the 80s or so, there were computers that were designed so that you could enter in data in a particular type of memory, which would tell you what each operation meant. So if you had one program in this memory, one particular operation might be an addition. A different operation might be a multiplication. And you could design the machine so that it was so that the same operations could be used interchangeably. So in one version of the computer, you'd be using an operation that was called addition. In a different version of that same machine, using that program in it, it would instead be using a copy. In a third version of that, it would be using that same instruction as a multiplication. So this was a very flexible kind of machine, and this is the one that Turing built during World War II for the post office in Britain. But von Neumann was thinking a different way about computers and robots during World War II.
Did I ask a question?
Sure.
For a moment. I stepped away briefly, so I don't know if you covered it. I don't think you did, but okay, you had your table up with the 16 components. I'm using the wrong word, that they've now settled on. Yeah, that's the table. And so a certain combination of bits creates an A, and another one creates a B. However, what I guess what I'm and you said that that the 16 that are now in use covers everything that we need, including emojis, and emojis, of course, are graphics. So what I'm thinking is, with this structure, how it tells the computer what letter you're looking for, but how does it tell where to place that letter? So in order for, the same letter to, letters to not be typed one on top of another on top of another, has to be placed somewhere in space or in somewhere on your monitor.
Well, in this case, they're the paper tape. Each 5 bits is a string of holes in the paper tape. And each letter or a space is, so you've got various kinds of letters, and then there's a space. Letters, there's a space. So your entire message is a collection of letters and space, and you type them all out in a paper tape. In the 1930 teletype, they were both simultaneously punched a hole, and they were via fixed wires sent to a Western Union office. And if it wasn't it would be the closest one, and that machine could punch a tape on its side, and they could then put it back through and send it to a different machine that they were connected to. So
I guess, okay, I don't know that you're addressing exactly what I'm talking about. I guess what you're saying is the nature of the machine that received the code, when it got to the end of the line, it would automatically move back to the beginning and one line lower. That was the nature of the machine.
Well, the machine you'd send a set of bits. The bits would received at a teletype at the other end, and it would punch the paper tape, and on it, because it was using the letters, it also had a typewriter built into it.
Okay.
And it would print the letter on a piece of paper.
Okay, so it had a typewriter characteristic to the machine that would automatically hit the carriage, or I mean the
it would print the
version of hitting the
carriage. Paper, yes. Well,
okay.
It was in 1930. It was literally a typewriter.
So in the case of something like an emoji or any other graphic, the only way that I can see that it could be done is by pixels, dividing your entire area or screen, in this case, into pixels, and having.
Well, remember, you only need a way. In essence, you only need a number to send the information to another machine, and it's got a table that when it sees that number come in, which is a string of bits, and in ISO it's 16 bits. So when those 16 bits come in, they're a number. And there's a table in the machine that receives it that says this number is this emoji. And that emoji gets sent, your phone is a computer. So it's got a table that has all the emojis in the computer in your phone. And when it receives that number, it goes, oh, that's this emoji. And it takes the bits and puts them on your screen.
Oh, okay. I understand. That's kind of like sign language. You can have a certain sign that means an entire word or phrase, or if you have a word or phrase that there is not a sign for, you have to kind of spell it out. So in the case of a graphic that's not an emoji, and there is no equivalent, this code means that thing, and you literally have to spell it out, you would have to, on line 1, have your code that everything is 0 except for a 1 in one place, and then your carriage goes down to the next line, and you have your 1 maybe a little bit off to move that line, so that you're in effect drawing a code for drawing, I guess is what I'm asking about. And that's the only way
Not
I
in
can
ISO. ISO has a one-to-one, an isomorphic table that says this number means this either symbol, character, formatting, all kinds, anything you need to know about using it in the computer, that's in a table in the computer. And it's got 146,000 items in the table, and they're isomorphic, one-to-one. And so once you find the number coming in from another computer, either using the internet or using Bluetooth or whatever is coming to you, Wi-Fi, you name it, then it knows immediately what that symbol coming in means. And it just, instead of showing you the number that came in, it gives you the symbol that corresponds to that number.
I understand what you're saying. I guess I'm talking about I mean, we have artists who are now making very fine artwork on computers. And there certainly is no symbol for their entire creation, which they're creating as they go.
Actually,
So,
there is all of the programs that those artists use have specific information about how much pressure you're putting with your pencil equivalent on the screen. It's got the number of bits by the number of bits on the screen that you're typing. It knows about color. It knows all of that information is collected as it's being drawn by the artists and collected in a file. So that file at the end can be rerun and completely reproduce every action taken by the artist.
oh, that's interesting. Okay, I think that answers my question.
Lee or Bob,
Thank you.
one thing that might make sense to you is when you type like a letter T in your computer, that T is actually, the computer knows you want to type a T, but it needs a lot more information before it can present that T on your screen. it needs to know what font, it needs to know what font size, it needs to know where it's going to go. So there is both the program, which in the case of the original example was integrated with the paper tape and the machines that was reading it. But in the computers today, there's a lot more overhead involved in taking that bit that comes, or that byte that has the coded letter that's telling you what letter you want, and then where that letter eventually ends up, what it looks like, what color it is, all that other information is additional overhead. So it's pretty complicated.
Right. But it's no different than all of the information for writing, for, you know, creating the picture by an artist.
Right.
They need
exactly.
to know the pressure, they need to know the color, they need to know the initial point that they started the stroke, and as they went along, every pressure, as either up or down, you know, greater or less as they went along. When they switched to a different color, you have to remember all of this information, formatting information, but each program has its own structure. They're not standardized the way ISO is. ISO is 147,000 or 144,000, whatever number of symbols that have been agreed around the world to use these symbols, these numbers, to be these symbols. That's not true in general. I mean, the way in which Microsoft does it is different from the way Apple does it. So the operating system matters in terms of the information you've been talking about, and about those artist programs. Each one has its own structure built for that formatting. It's not standardized. I've been talking about standardization. Now, each program designer creates their own internal standards, but they're not universally used by every programmer. That's the difference. Okay. So, as I said, Turing was designing a much more flexible computer, one where its operations could be designed at the beginning of a program and change the way in which the machine worked internally. But von Neumann was thinking about computers and robots. And one of the questions that von Neumann considered was, would it be possible to build a self-reproducing machine? So let's assume that a robot exists in a warehouse full of machine parts. The robot moves around grabbing components from the shelf and puts them all together. Eventually, it assembles an exact duplicate of itself. Johnny, all of von Neumann's colleagues called him Johnny. Johnny asked, what would include such a machine? How would it work? Well, if you wanted the robot to always be able to assemble an exact duplicate of itself, there would have to be a blueprint of itself. So would the complete set of instructions also include a blueprint of itself? Um, that raises a deep question. Does a blueprint of the robot contain a copy of the blueprint in the blueprint itself? If you remembered the work that Lukowski did on fractals, we've seen these structures before. They're called fractals. And fractals are always infinite in some way. They have infinitely fine levels of detail. Uh, Sorry, had a phone coming in. Anyway, fractals are always infinite in some way. The Julia set is shown here. We've gone down through it in long detail in one of our previous lectures. And you see a picture inside a picture inside a picture as you go down to an infinite depth. You can go as much fine detail as you want, and you'll see another copy of it somewhere else in it. That's the fractal nature. So memory in a computer has to be finite. It won't work for our von Neumann robot. So it can't hold a blueprint containing a little copy of the blueprint itself, and so on to infinity. Von Neumann decided that his machine would work in a different way. He used the two-sided nature of information. The blueprint is a program that tells the program how to construct its duplicate. The program can also be just another data file that can be copied and transmitted. So if the last step of the robot building program would say, make a copy of the robot building program, the blueprint, in the new robot's memory, the self-reproducing program doesn't have to be infinite. It just has to refer to itself. And this is known as recursion, and was fundamental to Turing's work. And he showed Gödel's theorem in computing using recursion. Anyway, that's a slight aside.
Bob,
Yeah.
in the machine I spoke of before with the magnetic delay line, the acoustic delay line, the Programma 101, it had a square root hardwire capability, but in order to get trigonometric functions or logs or anything like that, it did recursion. It would have you could set up these little subroutines that would go on and do a sine or a cosine or what have you, using these recursive things you just spoke of.
Oh yeah, and recursion is very important in finite Fourier transforms as well. It's used tremendously. Anyway, but that, as I say, is a somewhat of an aside. So someday, nobody's made a von Neumann machine yet, but someday physicists or engineers may make one. But those kinds of robots exist in nature. They're called biological organisms. They acquire energy and material from their surroundings, the great majority of which is sunlight, but they also use sugars and many other things in their surroundings, and produce offspring with the same basic design as themselves. So von Neumann's insight is significant about how information works in living systems. And we know that the little blueprint we've been talking about in an organism is contained in its DNA. So everything that von Neumann struggled to try and understand, nature did long ago, beat us to it a long time ago. One of the fascinating connections between information science is found in physics. Physicists have shown that information plays a fundamental role in the basic laws of matter and energy. Why do I say that? Well, a partial answer is that information is a general way of thinking about the nature of events, that is, cause and effect. And that is essentially what physics is about, cause and effect. So suppose we communicate a message. The message is sent and received. It went through some medium of transmitted signal and every sort of physical cause and effect link. This process can be recorded as a kind of information, a kind of communication. In the 20th century, physicists regarded nature as a complex interplay of forces and energy transformations. In the 21st century, physicists regard the nature of regard nature as a complex network of information. And our understanding of physics is influenced by the concept of information, just as the concept of information influences physics. Now, John Wheeler, who was a great slogan maker of physicists, was way ahead on this. He had the idea in a pithy slogan, "It from bit." It might be that everything in the universe, everything it, actually emerges from an underlying information process. Of course, he was talking about quantum bits, not the bits we're talking about, but still a very interesting insight. Okay, so that's the introduction to information without mathematics. We'll do more of that next week, but I'm going to start with Maxwell's demon, and this is going to be fairly short because I didn't have enough time to finish everything that I wanted to do this week. So Maxwell's demon is a Gedanken experiment. One of the great results of the 19th century was the discovery of the abstract state function entropy, which we talked about last week. Entropy describes equilibrium in thermodynamics, enabled physicists to understand the behavior of irreversible processes. The great result was the second law of thermodynamics, namely that entropy only increases. The result is that you can't have two containers of gases in equilibrium to do work. Well, is that true, or is there a process that maybe comes around it? Maxwell imagined a container with two parts, A and B, and they were both parts were filled with a gas at the same temperature. So the whole system is in equilibrium. And placed between them is a wall. So they both have the same Maxwell distribution of speeds. And there is, however, an imaginary demon here who is able to move a microscopic frictionless trapdoor in the wall between the two sides. So if there's a molecule coming through, he could open it and if he doesn't want to, he could leave it closed. And so if it's closed, it'll bounce back. And if it's open, it'll go over here. All right. When a faster than average molecule from A flies towards the trap door, that's why it's red, the demon opens it and then lets it fly from A to B. And similarly, if the trapdoor can go both ways, or if you move it, if you slide it up so that it's open, whenever there's a cool molecule aiming this way, he can open the slot and let the cool molecule move to the left. So when you did this over and over and over again, you'd wind up a cold gas in A and a hot gas in B, and therefore you would be able to work contrary to the second law of thermodynamics. So this was a Gedanken experiment that obviously is an idealization, but there's no reason why it might not work. And the whole Gedanken experiment seems to negate the second law of thermodynamics. Physicists have worried about this for more than 2 centuries, and unfortunately, I'm going to discuss this more next week because I didn't get a chance to finish the work that I was trying to do. So, is there any further questions about either Maxwell's demon or information theory, the introduction of which I did this week?
Just one point. 2 centuries would take us to 2050. We're not quite there yet.
Okay.
How about 1 century and some?
Okay, I rounded up. But you're right. You're absolutely correct.
Well, thank you.
Well done. Yeah, enjoyable.
Okay. Well, this is all the background and history, and we'll get more into the mathematics of it next.
I didn't quite understand. I'm sorry, I was chattering away on mute. I didn't quite understand the picture that you just showed with Maxwell's demon because all of the hot molecules ended up on one side and the cold molecules on another. And that means the two sides are out of equilibrium and work can happen.
Right.
So I didn't understand the point.
That is the point. According, that would lower entropy rather than increase it.
Yeah,
So that would break the second law of thermodynamics.
I thought that, okay.
I mean, that was the great insight and discovery of the 19th century, that you could only create things that were that were not in equilibrium. If you let them open, they'll only become equilibrium. The entropy will always increase. This is a process that does it the other way, which it says you can't do. This would decrease entropy.
I see. It's a mechanical manipulation of what you have. Okay, I understand.
Okay, yeah. So that's it's a Gedanken experiment, how you would do a physical process that requires, somebody who's amazingly able to take a look at the velocity of every one, notice when one was coming towards the trap door, and if it was coming in one direction, open it and let it in, close it. If it's coming from the cold one, go in the opposite direction, open it and let it in. But this is something that, according to the second law of thermodynamics, is impossible. So that was his Gedanken experiment, and we'll start with the Slizard engine, which is the simplest possible way of doing Maxwell's demon, and talk about what Slizard said, although he wasn't accurate in his assertions. Again, assertions, not proof. And we'll talk about much more and get into more on the underlying mathematics of information.
I have one question about whether this might relate to, it looks a little similar to what you're showing, but I've always wondered if gravity in a body like the Earth moves heat to the center of the Earth. And that would be simply, if it collides going up, it would have less energy than if it collides going down. And I just wondered if that moved heat to the center of the Earth. Maybe that's something well known, or there's some principle on that.
Well, it is. It creates heat, but the creation of heat is not a problem. It still increases the entropy of the entire Earth because the process that creates the energy uses more energy than it creates in the form of heat. And that's still following the second law of thermodynamics. So as long as the process creates more energy, uses more energy than it creates, it's not a problem.
Okay, I will think about what you said there. Thank you.
Okay. Steve, you want to add a comment? I guess not.
I think he's gone.
Ah,
Or
okay.
I don't know if he's gone, but I don't see his picture.
Okay. Well, if that's it, if there's not any more questions, I'm going to, first of all, stop the share. And second of all, I need to stop the recording.
Thank you, Bob. This was
Thank
very
you.
interesting.
Yes, thank you very much. You guys have a good week.
Okay.
Thanks a lot.
Steve.
Great lecture.
Bye, everyone.
Bye-bye.